So, we will continue from operational energy, that is what we looked into, and we said that it is a U value or thermal conductivity, which is very important in terms in terms of material properties for mechanically conditioned building. This is for conditioned building. Of course, if it is unconditioned building, then we would like to maintain comfort condition. In that case, essentially thermal capacity is also important, because there will be some storage in the wall system, wall or roof or ceiling, or the envelope part, there will be some storage in this. So, it will be stored and released later on. So, there is a time difference between maximum temperature outside and when its effect enters into the internal space. So, that time difference is what we express in mathematical form in some manner called time lag, and there will be decrement temperature inside that would cause a heat flow. That heat flow would be its amplitude would be, there will be some reduction in the amplitude if you look at the heat flux outside. So, there is something called a decrement. So, we define, we basically we like to, in places where you have got high temperature variation outside, we would like to keep decrement low, that means ratio of heat coming in by temperature outside in terms of the fluctuating temperature, that should be low. And also we would like that there is a time difference, because night temperature becomes cool in desert and such things. So, we are not interested right now in this, because energy consumption, when we are looking at, we are trying to look at energy consumption, right. But for unconditioned building, of course, you have to look into these issues also. At the moment, we are not interested in that. Similarly, the surface properties, long wave emissivity and short wave absorptivity. Sun's rays falls onto the surface, sun's rays falls onto the surface, right. Sun's rays falls onto the surface, let us say, okay, sun's ray fall onto some surface. Now, how much of it will enter is a function of surface characteristics. How much of it will be absorbed is a function of surface characteristics. For example, a whitewashed surface will not absorb much. Black will absorb, black absorbs more. Blackened surface absorbs more. So, what we call alpha value, absorptivity is also an important thing, but once it gets heated up, it also emits that energy out, and that is we call long wave emissivity. So, these properties are also important, these properties are also important. I think that is where we stopped. Long wave emissivity and short wave absorptivity, these are important. Now, therefore, what is important is what is U, and I think in the last class I was saying 1 over U is equals to something I defined called surface conductance. I think last class I did this for our one side, and then we said that it would be sigma Li over Ki, or rather this should be written in this manner, not this, sigma of the whole thing, sigma for different, supposing I have got number of layers, number of layers, right, one layer of the brick, plaster, other layer, etc., etc. So, I going from 1 to n plus 1 by Hi. So, you see the conductivity of the material plays an important role in this property, which is called transmittance or U value. Higher the U value, more heat will be transferred, because we saw in the last class Q is equals to U A into delta T temperature difference between two sides, two surfaces, this side and that side of the wall, it may have, including the air temperature here, air temperature here. So, this is the heat flow. Therefore, higher U means more heat flow for the same temperature difference, and we would like to keep it lower. So, insulation is 1 by U, and for that K should be lower. So, K is the important property, that is why we are looking at it at the moment. We look at a little bit into another property, that is density into specific heat, which is volumetric heat capacity. We will look little bit onto this also. So, some understanding of thermal properties are important, right. So, we are looking at this actually, because U value will be controlled by this, right. All right, the factors which governs the thermal properties or thermal conductivity, because most of our materials are porous, most of our materials are porous. So, we have solid and we have some pores, and porosity and arrangement of pores with respect to the solid is important, right. Okay. So, the arrangement also we shall see that how it works, and this is very important, moisture content, right. Okay. Why moisture content? Moisture content, why? Because pores will get filled by water, filled with water, instead of air, in place of air. So, replaces air. Conductivity of air at normal temperature is air, K air is something like 0.025 watt meter Kelvin, and conductivity of water, liquid water, is it is 0.6 or so watt meter Kelvin. So, you can see it is about 25 times, it is nearly about 25 times more. Water conducts nearly about 25 times more, 0.025 multiplied by 25 will give you, around 0.625. So, it conducts more, Therefore, when the pores are moist, saturated it will conduct, and also partially moist it will conduct. So, let us see the mechanisms. So, let us see the mechanisms. Mechanisms are conduction through the solid, conduction, there is possible convection and radiation, and evaporation condensation in pores. For example, in the hot phase, this is let us say hot side and this is cold side. Now, water here might evaporate, if pores are filled with water, water might evaporate, travel to this place and condense. When it condenses, it will release that heat. So, it will actually absorb heat while evaporating, and while going to the other side where it condenses, it might. So, the transport, it might, this could be another parallel path, right, evaporation condensation in pores, this can also occur, right. So, these are just. So, what we talk in case of porous material is a equivalent thermal conductivity of such material, Ke. So, most of our materials, brick, concrete, lightweight concrete and similar ones, they are all porous materials. Even timber is porous, and insulating materials are deliberately porous. Some of them will make it deliberately porous, but if I understand the mechanism, then it becomes easier to look into that. So, people, since it is function of porosity, higher the porosity, conductivity will be low. Higher the porosity, more air, less conduction through it. Let us say in dry state, higher the conductivity, porosity will be low. So, people try to relate it to density simply. A dense material conducts more and a low density material will conduct. So, lightweight aggregate system, lightweight concrete and so on. So, dry density, if I look at it versus thermal conductivity, as density increases, conductivity increases. This is empirical observation, and people try to relate some empirical relationship. So, typical variation of thermal conductivity with density. This is for bulk, all the material people have been trying to deal with this, not looking into details. However, if you look at the porosity versus thermal conductivity, for materials such as brick, concrete, brick, concrete or different different let us say different different pores or different porosity values. So, which would mean a weak concrete to a somewhat denser concrete. So, if you look at it, then aerated concrete were deliberated foam concrete, where you create pores deliberately by adding foaming agent. So, this foams creates closed pores, fly ash bricks or similar sort of thing. Their porosity will vary with thermal porosity increases, thermal conductivity reduces. Now, here you can see that porosity can be as high as 80% or so in foam concrete or similar sort of thing, and in somewhat denser normal concrete could be somewhere around this. So, conductivity varies between this sort of range, but if it is saturated, this range increases, it goes to 4 here, and this is surely the lower range increases. So, saturated conductivity, saturated in the moist condition, the range shifts. So, there is an increase in the conductivity, this has gone to around 4.5 from 3, and this is also gone higher up from here. In fact, the rate of increase will be more there. So, moisture plays a role, saturated state and dry state, there is a difference. Now, early work, as I said, thermal conductivity was related to moisture content through some multiplying factors. So, these are called Jacobs multiplying factor. This you find in books of 1950s or 40s, around that time. They just simply said that if you have moisture content by volume 1%, multiply by a factor of 1.3, 2.5 volumetric moisture content. That means, volume of moisture divided by the volume of dry volume of the solid, right, which would be same. Basically, volume of the solid, after all, this porous material. So, it is a bulk volume, it is bulk volume actually, bulk volume. So, volumetric moisture content, not mass basis, and that is what it is. So, that is why you find 25%. So, these are multiplying factors. So, if you know the dry conductivity, you can actually multiply this. Now, what are the mechanisms? First of all, mechanism is conduction through the solid, and there can be convection and radiation in the pore. But this is very small, because convection is a phenomena whereby molecules move and then circulate, and through circulatory motion it transfer the heat. Hot molecule will go and cold molecule will so this kind of thing. So, in such situation, if the pore sizes are small, then this does not occur. This is a function of the temperature difference between hot and cold surface. In a small sized pore, this temperature difference is very small, and even so, pores less than 0.3 millimeter, 3 millimeter you do not get that, 0.3 millimeter means 300 microns. So, pore size is less than you are unlikely to get anything, and you will not get much of it in a closed pore system, convection so transportation. So, these are neglected in normal ambient condition, but if you are dealing with high temperature, then this becomes important, especially when porosity is very, very high. So, conduction through the solid is the main thing, and conduction equivalent conduction through the pore, which is a function of mainly as a function of moisture content, not much of a function of radiation and all that. So, people try to do what? Some modeling, they assume Ohm's law model. That means, this is the length of the pore, conductivity of the pore, and heat is flowing in this direction. This is the solid slow series model. So, heat flowing from this direction. So, this is your solids. For example, all pores are arranged in this form such that I have solid, then pore, maybe there is a solid and pore. So, these are in series. So, if this is in series, then simply it is something similar to U, what we did. Total length will be Ls plus Lp, right, and Ls plus Lp divided by K equivalent. How is K defined? K is heat flux Q divided by A, K T2 minus T1 minus T2 divided by L. That is what we said. So, L by K, right, same heat is flowing, same formula. So, if this is T, this T1, this is let us say T2, this T3. So, T1 minus T2 divided by, so K is solid divided by L solid, and area is same, must be equals to K of the pore T2 minus T3 divided by Ls, and equivalent conductivity will be defined as Q into A into K equivalent divided by Lp plus Ls into T1 minus T3, right, T1 to T3. So, if I again do the same thing what I did in the last class, T1 minus T2 would be given as T1 minus T2 will be given as Q by AKS into L of the pore, or L of the solid plus Q into Q by A K pore. This is the plus T2 minus T3, let us say, will be, and this will cancel out, T1 minus T3 will be then this into L pore plus L Q into L pore divided by A, already I have done that. So, this can be written as Q by A into Ls by Ks plus Lp by Kp. T1 minus T3, if I do a little bit of algebra, that is what I will get. And this doing this therefore, what will be equivalent conductivity? Equivalent conductivity will be Q by A is equals to given by this formula. So, this is the same flow which is taking place. So, one can write it like this. So, equivalent conductivity one can derive from this one, and that is what is done here. So, this is this you can rest all things at Q by A will cancel from everywhere, and T1 minus T3. So, this should be equivalent conductivity can be written in this manner in terms of Lp plus Lp by Kp plus Ls by Ks, etc., etc. So, equivalent conductivity can be written in this manner. Now, what is this Lp by Lp plus Ls? This is the proportion. If the area is same, then this can be written as, this can be simply written as this is basically Lp by Lp plus Ls is nothing but porosity. If the area is same, because this into A, this into A, right. So, this is a volumetric volume, so the volume of pores divided by total. So, this can, therefore, one can write this as 1 by Kp, this is porosity, this is the volume of the pore, porosity, and this is the volume of the solid, which is 1 minus P. So, when you have series model, you can simply write, if you take this, if you take simply 1 by Ke, this part 1 by Ke is equals to P by Kp plus 1 minus P by Ks. If it is series model, if all pores are just they are solid, then pore, and again solid, they are in layered form. But in real system they are not layered form. People tried to do that in the beginning because Ohm's law concepts were available. This is one way to look at it. So, Ke can be written in this manner. If I write it from this one, Ke can be simply written, because Ke, this is equals to 1 over Ke. So, Ke can be written as Kp Ks, you take Kp Ks, Ks multiplied by P, Ks multiplied by P, and Kp multiplied by 1 minus P. So, K can be written in this manner. Now, look at this, if the Kp is very small compared to Ks, which is the case for air, then this term will, this term will be negligible compared to this term, right. This term will be negligible compared to this time, and simply K will be given as, and Ks will cancel out. So, this is going away and Ks will cancel out with this, I will be left with Kp by P. So, for series model Ke is equals to Kp by P. So, whatever conductivity of the pores divided by P, right. Now, this gives you a very relatively small value, because you can see that Kp is 0.025 as I was saying, divided by porosity, let us say 20%, this is the value you will get. So, this is one. People try to look at the other model, because this is one way of modeling, the other could be parallel model. Parallel model is, now I have got area, this is the area of the solid and this is the area of the pores. So, the Q should be divided into two parts. Some heat will pass through this, some heat will pass through this. So, the total Q will be given by total Q, okay, let me just write it, Q would be given by AP into Kp, right, AP into Kp into temperature difference. Now, temperature difference is constant here, T1 minus T2, T1 minus T2, that is Q1 or Qp, let me call it, and Qs would be As Kp Ks T1 minus T2. Total heat Q is the sum total of all this. So, Qp plus Qs, which will be equals to AP plus As, I can add this up, right, or AP Kp, I mean AP Kp As Ks into, this is not common, this is T1 minus T2 is common, T1 minus T2 is common, T1 minus T2 is common. So, I can just do this algebra, and therefore, the equivalent Ka will be given by this, equivalent Ka will be given by this, equivalent Ke into A, equivalent Ke into A is this value. So, that is what I am doing, summing up the heat flow through each one of them, and then I get AP plus As into Ke must be equals to this. In other words, then Ke I can write, divide this both by AP by, and since the length is same, this represents nothing but the porosity, this represents 1 minus porosity. So, the law is Ke is equals to P Kp plus 1 minus P into Ks, and this will be, if this Kp is very small, this will be neglected. So, this would be given by simply this. So, you get two cases, this value will be definitely very high and the previous value was small. So, in fact, what it gives is range. So, this is what it is. So, Kp is very small, therefore, parallel models yields much higher value of Ke and series model much smaller value, depending upon ratio of Kp by Ks. These two models represents lower and upper bound of conductivity, because in material there will be neither porous, I mean neither parallel nor series, but they are the upper bound and lower bound. So, one can use combinations, that is what people try to do sometime, you will find in some of the books, you will find combinations, for example, they will like to put some factor. So, combinations would be Ke would be something like some factor, let us say lambda into let us say Kp into like the model that was there, Kp Ks, we had two models. So, you can just take from here, we can take from here, this one we can take. So, K equivalent was given by this multiplied by lambda, this multiplied by lambda, and rest one is 1 minus lambda multiplied by, this would be a K equivalent when you have a combination, then it will be something like this, right, or let me write it separately in the next one after this. So, one can write it like this, Ke will be equals to lambda Ks Kp divided by 1 minus P into Ks plus P into Kp, that was the thing, plus 1 minus lambda into P into Kp plus 1 minus P into Ks. I think I should write like this. So, this kind of also has been attempted, but then they do not work. Again you have to find out what is the proportion of series and rest all is parallel and things like that. So, it becomes difficult. So, there is another kind of thought process went into thermal conductivity, because if you can look into more details, more and more it becomes important, details of this behavior becomes important. So, that is why approximate medium approximation, this is called EMA, stands for effective medium approximation. EMA model, that actually came from, if I have a spherical material, an inclusion in spherical inclusion in otherwise bulk material, the disturbance of the magnetic field, electromagnetic field by this inclusion was derived by Maxwell. So, based on this effective medium approximation, therefore, the net flow or analogic to electric field is a temperature field. There is a temperature field in the bulk. If I have another material, this temperature field will get disturbed. So, therefore, the heat flow through this would be disturbed due to presence of another inclusion, right. So, this effective medium approximation concept takes care of that, right. So, the disturbance of the temperature flow field flow path, because it has to flow, heat has to flow path, heat flow path, it will be disturbed through this, and based on this EMA models are conceived. So, this gives you K effective is equals to, there are two component here, one is a dispersed phase, another is a continuous phase. The bulk one is a continuous phase and dispersed phase is the other phase material. So, the equation that one of the equations it is there, and this is what is used in thermal conductivity. Kc, if you assume so Kc is a continuous phase, this is the conductivity of dispersed phase, and this is how 1 minus P, P is the proportion of the dispersed phase, which is something similar to porosity. So, that is how it is given, Kd plus Kc, this is Kd 2 Kc 2 1 minus P, and no, there is something wrong, because this will become 1, there is something wrong. Subscript C refers to continuous and dispersed phases respectively, because there is sign differences. So, here is a minus is fine, this plus. So, this is how this plus. So, this is how it is actually. Subscript C and D refers to continuous and dispersed phase. Hence, one can consider pores as dispersed phase in solid, and that is how the equation will be, this is plus, this is minus. So, this you can see that this is what this will be some proportion of the Kc, some proportion of the Kc. Solid dispersed in, now other case could be solid dispersed in pores, that means less low higher porosity scenario, all pores are interconnected and you have some pore scenes, solid scenes, right. So, if this solid dispersed in pores, the equation will become K solid 2 Kp, because continuous the equations were something like this continuous 2K continuous K dispersed. So, if the solid is dispersed in pores, then it will be something like this K solid, and that is of the pores, and 2 porosity is anyway very much there, plus Kp minus Ks, this is the for the dispersed phase, this was the continuous phase. So, if I neglect this, then I will get slightly simpler one, and this is related to P. So, I will get simpler one, and if I look similarly, pores dispersed in solid. So, this is the brown one is my solid, and there are some pores, and then Kp 2 Ks. So, this time this is dispersed phase. So, therefore, Kp here, this is the solid phase, this is the continuous phase, and this is what it is. So, you can see that this will again give you higher value, because a fraction of Ks, and that will give you again solid dispersed in pores, highly porous material, it will be a fraction of the conductivity of the pores, right. So, one can get upper and lower bounds of thermal conductivity with these two models again. So, Ke is equals to Kp, that is 1 minus 2, rest all you neglect the in this equation you can neglect these phases, Kp can be neglected in comparison to Ks. So, this becomes plus etcetera. So, it gets neglected, you can neglect this Kp, even neglect this Kp. So, you will get Ks plus 2p into Ks, 2p into Ks divided by Ks plus 2Kp 2p, right. So, one can, it will be simply Kp extreme cases. So, you can see that. So, there are two, again I can get two ranges for n, this is what I will get, p divided by 2p minus Ks. So, this by neglecting the Kp's with respect to Ks, I will get something of this kind. So, this two gives again upper bound and lower bound. So, none of them give. There are better models which tries to, I mean there are these bounds are looked into in more details, especially the similar models are available for elastic modulus, because equations are similar. Supposing I have got a material series and parallel, two materials, I want to find out the equivalent modulus of elasticity. So, models like Hashin and Strike-Spence model, there are many models which came which gives upper and lower bound of similar materials. So, I think we will look into this, but then we can have 3D models as well. There are several kind of concepts, I will just give you one.